I can finish this up. So the difficulty with this is, so we've got this symbolically, this model, and it's great. The difficult thing is always to estimate these parameters. That's why I said the rub is estimating the parameters. So you have to estimate what R1 is, R2 is. Sort of theoretical predictions from geometry, fluid type, and all that. And we can do it from spec sheets for, say, the generator. But oftentimes we have to measure some of these explicitly. So we might need to do some parameter estimation, which is an entire field, but you can do set up simple experiments to measure some of these. And yeah, so there's a lot to that, but suffice it to say that it's nice to have this model. This is great. And if you were designing this, you could tweak these and see what type of performance you get out of it based on a simulation model. So it's a pretty powerful model, and it really wasn't that. So this is just telling you where to find the Mathematica script that I used to do the algebra on GitHub. And, you know, really writing down, essentially what it came down to was writing the linear graph model. Once we had the linear graph model, you know, applying our normal tree, finding our state variables, finding out that it's sixth order, and then writing our elemental equations, which are pretty straightforward. They're always the same. And then writing our continuity and compatibility equations, which required a little bit of interpretation, but straight out of the graph. And then it's just algebra to simplify it down to a state model. So, and then we know all kinds of things. We could find a theoretical solution. We could find a numerical solution. We could find a simulation numerical solution. And then we could also do find the eigenvalues, for instance, see where they lie, see what type of responses we're going to get from this system. How does the system respond to a sudden input in, say, one of the, like the flow rate, sudden, maybe runoff from